Hello, my name is Alexey, and this video will hopefully become the first in a whole series of videos focused on TOK concepts. The idea behind these videos is to provide an explanation of the important concepts that underlie the TOK course, and that you will be very likely to use in your TOK exhibitions and especially your TOK essays, and to provide these explanations in a way that is simple but not simplistic. In this particular video, I will talk about the demarcation problem. How can we tell the difference between science and non-science? I will explain the verification criterion, the idea that science, unlike non-science, is based on experimental evidence. I will also explain why this idea is wrong. And I will talk about falsifiability as something that is accepted currently as the standard of scientific knowledge. I will give you two cool specific examples of this, one about Freud and one about Einstein, and I will explain which one of them is science and which one is not and why. Finally, I will look at the recent prescribed essay titles from May 2021 and discuss how and where you could apply the concept of falsifiability in these titles. This will hopefully show you how relevant and how central the concept of falsifiability is in the entire TOK course. You can always use this navigation screen to see where we are and skip to the part that you find most useful. Falsifiability is the idea that a statement is scientific if, in principle, it is possible to prove this statement wrong. For example, the statement, the boiling point of water is 100 degrees Celsius, is falsifiable because, in principle, it's possible that I will conduct an experiment that will or carry out an observation that will prove this statement false. Therefore, the statement is scientific. I'm not saying it's true, I'm just saying that it's scientific, that is, it belongs to the domain of science. On the other hand, the statement like God exists is not falsifiable, because I cannot imagine an experiment that would prove this statement wrong. Therefore, it's not a scientific statement. Once again, it doesn't necessarily mean false, it just means it's not science. Think about this. How can you tell the difference between science and non-science? There has to exist some kind of criterion or a set of criteria, some essential characteristic that science always has, but non-science doesn't. Multiple such criteria have been proposed in history, but none of them seem to work. For example, you can say something like, science uses precise measurements. But then many non-sciences and pseudosciences also do. For example, astrology, a study of how stars influence your destiny, use precise measurements. So this criterion doesn't really work. The problem of drawing the line between science and non-science is known as the demarcation problem. And the challenge has been to find one reliable demarcation criterion, something that science always has, while non-science doesn't. One demarcation criterion that became really influential in philosophy of science at some point around 100 years ago is the verification criterion. It says that scientific claims are supported by empirical evidence or observation, whereas non-scientific claims are not. It is a very common belief among people not familiar with theory of knowledge, and a very common thing to say when you ask students to explain what makes science different from non-science. All the more fascinating that the verification criterion is actually wrong, or rather fundamentally faulty. It is based on a logical fallacy known as affirming the consequent. And it can be written down like this. If P, then Q, Q, hence P. For example, if it rains, rooftops are wet. Rooftops are wet, therefore it rains. Or, if my theory is correct, then this observation will support my theory. This observation supports my theory. Therefore, my theory is correct. The problem here is that one word is missing, a small but an extremely important one, the word probably in the conclusion. The thing is, rooftops may be wet for some other reason, unrelated to rain. It is possible, theoretically, that some children were throwing around balloons filled with water, or that a giant poodle was passing by and peed on the roofs. I said it was a theoretical example. In any case, this logical sequence can only lead to probabilistic conclusions, such as probably P, but not certain conclusions. This is what I should have said. If it rains, rooftops are wet. Rooftops are wet. Therefore, it probably rains. Or similarly, if my theory is correct, then this observation will support my theory. This observation supports my theory. Hence, my theory is probably correct. This shows why looking for evidence that would support your theory is a useless endeavor. If something is supported by evidence, it doesn't necessarily mean that it's science. Non-sciences are also supported with some amount of evidence, and actually, they bring it up all the time to support their claims. In a nutshell, verification is one lousy demarcation criterion. Karl Popper in 1963 proposed an alternative demarcation criterion that is widely accepted today. It is known as the falsification principle, and it can be summarized like this. A theory is scientific if it attempts to find refuting evidence for its claims. A theory is not scientific if its claims are not falsifiable. That is, if it is impossible to carry out a study that could potentially prove the theory wrong. We accept scientific knowledge as provisionally true if we try to refute it but would fail. We can only reject theories with certainty, but we can never prove a scientific theory. The logical strategy that underlies the falsification principle is known as modus tollens, or denying the consequent. And it looks like this. If P, then Q, not Q, hence not P. For example, if my theory is correct, then this observation will support my theory. But this observation does not support my theory, not Q. Hence, my theory is certainly incorrect. Or, if it rains, rooftops must be wet. But I can observe that rooftops are not wet. Hence, it certainly is not raining. The big takeaway message here is that we can only refute scientific theories with certainty, but we can never prove them with certainty. There is no such thing as a true theory. But if that is the case, then efforts of scientists should be directed towards seeking contradictory evidence rather than supporting evidence. We should try to falsify our own theories. And any theory that is scientific must be, in principle, falsifiable. Now, my two examples. I will give you two examples that will illustrate the difference between falsifiable and non-falsifiable claims. Example one, Sigmund Freud. One of the things Sigmund Freud is really famous for is his interpretation of dreams. His iconic book was published in 1900, and it caused a lot of discussion. If you look at his dream analysis theory logically, you will realize that he was actually very straightforward about that and explicit about that in his book. That the whole theory is based on one fundamental assumption, that every dream is a wish fulfillment. In other words, we all have some unconscious desires, and our dreams, in this or that form, satisfy those desires. For example, you dream of eating a cake, but during daytime it's impossible due to some dietary restrictions that you have to observe. Well, when you go to sleep, you satisfy the desire fully in your dream because you eat the cake the whole night long. Sometimes it's not so obvious, of course, and then it is the job of the psychoanalyst, according to Freud, to decipher the dream and to understand which subconscious desire is being fulfilled in what way. This assumption that every dream is a wish fulfillment is so fundamental that if we reject it, Freud's whole theory of dream interpretation will collapse. In his book, he describes several cases in which a dream did not appear to be a fulfillment of any wish, and yet, through analysis, Freud was able to show that there was in fact a wish, and it was in fact fulfilled. One such example is Freud's former classmate. Let's call him Friedrich, although that's not what he was called. He was a lawyer, and he attended one of Freud's lectures. After the lecture, Freud's classmate went home and had a dream that he had lost all his lawsuits. It's a terrible dream for a lawyer. The next day, Friedrich complained to Freud about it. He said, "Do you really believe that it is my unconscious desire to lose all my lawsuits and fail my career?" And this is how Freud analyzed his dream. Freud knew Friedrich from before. He was Freud's classmate for 8 years. Freud was among the best students in class. Friedrich was always somewhere in the middle. It is natural, said Freud, that he was jealous. He became even more jealous when Freud became so popular in the world with his new theory of psychoanalysis. He attended Freud's lecture, sitting there and just being jealous. The lecture explained the fundamental principle of Freud's theory, that every dream is a fulfillment of a wish. The guy was not a fool. He realized that this assumption is what the whole theory rests upon. So Friedrich comes home and has a dream that is as far removed from being a wish fulfillment as possible. Well, says Freud, the fact that he had a dream that is not a realization of a desire is in itself a realization of the desire to believe that Freud's theory is a bad theory. In other words, says Freud, this dream tells my classmate that Freud is a failure, that his theory is incorrect, and that there's nothing to be jealous about. Do you see what happened here? Freud flipped the whole thing upside down and used it as supporting evidence. He had a piece of evidence, his classmate's dream, and this piece of evidence did not match his theory. In fact, it contradicted his theory. Freud took the evidence, twisted it in a way that made it a perfect fit, and used it as supporting evidence for his theory. In a sense, this makes Freud's theory of dream interpretation indestructible. It's hard to imagine what kind of evidence we must obtain to be able to prove his theory wrong. It is not falsifiable, and hence, according to the principle of falsifiability, it's not a scientific theory. Now, example 2, Albert Einstein. When Einstein published his relativity theory, it challenged many ideas existing at that time, and so some scientists found it very hard to believe. One of the claims of his theory is that light can bend when it passes near heavy gravitational masses. For example, that light from a distant star will bend when it passes near the sun. More accurately, it's not the light that bends, it's space itself, and light just travels in this bent space. Anyway, this sounded so incredible at that time, the idea that light can bend near heavy gravitational masses, because the idea that light always travels in a straight line was really well established in physics at that time. So Einstein looked for opportunities to test his predictions, and it was not easy. The sun is bright, so you can't really see any distant stars behind it. But finally, in 1911, Einstein realized that such observations could be made during a total solar eclipse. This is an astronomical phenomenon when during daytime, the moon completely covers the sun for a short period of time. So the sun is in the sky, but it's covered, so you can see behind it. And if you're lucky enough, and if it's not cloudy on that day, you can even observe some stars around it. The total solar eclipse is a rare event, and it is only visible from certain spots on our planet. The nearest opportunity presented itself only in 8 years after the prediction, when British astronomers Frank Dyson and Arthur Eddington organized an expedition to a small town in Brazil on the 29th of May 1919 to test Einstein's predictions. In other words, Einstein said, "Yes, I know my theory sounds very counterintuitive and maybe a little crazy, so let's try to prove my theory wrong. 8 years from now, on the 29th of May, this star must be here according to our astronomical calculations, but I predict that if you look at it on that day from this town in Brazil during the total solar eclipse, then you will not find it there. Instead, you will see it where I predict you will see it. And if you don't see it where I predict, then my theory is wrong." His prediction, by the way, came true. Astronomers saw the star exactly where it was predicted by Einstein, but not where it was supposed to be according to astronomical calculations. Now, does it mean that Einstein's theory is true? No, it doesn't. But this does mean that we have made an attempt to falsify his theory, that our attempt has failed, so our confidence in the theory increased. We will continue our attempts to falsify and refute the theory, and perhaps one day the theory will fall. But this day is not today. We can provisionally accept it as true until that day comes. So why is the concept of falsifiability so important in the TOK course? Well, in many ways, it captures the essence of methodology of natural sciences. And for that matter, when you compare natural sciences to other areas of knowledge, which tends to happen a lot in TOK essays, falsifiability will also naturally come up. So why don't I just show you a recent list of prescribed TOK essay titles from May 2021 and show you in which of the titles the discussion of falsifiability may be useful. Title 1. Accepting knowledge claims always involves an element of trust. Discuss this claim with reference to 2 areas of knowledge. The idea of falsifiability is suitable here because you can talk about how in natural sciences no claim is trusted and every claim is thoroughly tested. Scientists direct their efforts towards attacking their own claims, attacking as much as possible and from all possible angles. And at the same time, If after all these attacks the theory still stands, it does not mean that the theory is necessarily true. We accept it as true provisionally, and in this sense we put some trust in it. And this element of trust is required for us to move on with the scientific investigation. You could then look at some other areas of knowledge, say human sciences, and discuss how consistently the principle of falsifiability can be applied in those areas. Title 2. Within areas of knowledge, how can we differentiate between change and progress? Look, suppose we had a scientific theory and one of our falsification attempts has been successful. So we obtained some counter evidence and we're rejecting the theory. Have we made progress? On the one hand, we know now that the theory is false, so we have more knowledge than we used to have. On the other hand, we used to have a theory that nicely explained things, and now we don't, so we know less. This phenomenon is called Kuhn loss. It is these links to falsifiability, to paradigm shifts and scientific progress that can be explored here in this title, among other things. Title 3, labels are a necessity in the organization of knowledge, but they also constrain our understanding. Well, falsifiability is probably not the best concept for this title. If you think otherwise, let me know. Title 4, statistics conceal as much as they reveal. Probably not the best. However, I want to tell you something interesting in this respect. Not many people realize it, but inferential tests and statistics actually have the logic of falsification already embedded in them. When we test a result for its statistical significance, we have the null hypothesis, stating that the result does not exist. And we have the alternative hypothesis, stating that the result exists. Any inferential test in statistics is actually a test of the null hypothesis. We're trying to reject it. If we succeeded in rejecting the null hypothesis with a high degree of confidence, then we accept the alternative hypothesis. It's no chance that inferential statistical tests are designed like this. We try to falsify the null hypothesis, and if we can't, we accept it. By default, we assume that our theory is wrong unless we can prove otherwise. Title 5. Areas of knowledge are most useful in combination with each other. Discuss this claim with reference to 2 areas of knowledge. You could probably speak about how methodology is one of the things that defines areas of knowledge. Experimental research based on principles of falsifiability is the essential feature of the methodology of natural sciences. In mathematics, for example, the methodology is entirely different. It's based on deductive reasoning and axiomatic systems, and principles of falsifiability just don't apply. There's no doubt that mathematics is used in scientific investigation as a tool, and in that sense, the combination is helpful. But the methodology of mathematics cannot be applied to obtain scientific knowledge, and the methodology of science cannot be applied to obtain mathematical knowledge. So a combination is only possible to a certain extent. And you can use that as one of your cool counter-arguments in the essay. Finally, Title 6, avoiding bias seems a commendable goal, but this fails to recognize the positive role that bias can play in the pursuit of knowledge. You could probably talk here about how falsifiability and how bias is avoided in natural sciences, or in other words, how the logic of falsifiability provides a guarantee that everything has been done to ensure that there's no bias. It doesn't touch upon the positive role of bias, but it can still be used as part of the general argument in the essay. So in summary, in 5 out of 6 prescribed essay titles in May 2021, the concept of falsifiability could be used, if not as the central focus of the essay, then at least as one of the things that you could mention. I hope I have demonstrated that falsifiability is one of the very key concepts in the TOK course. If you understand falsifiability, you can bring up so many important claims and counterclaims related to so many aspects of knowledge. It links to such other concepts as evidence, certainty, truth, justification, explanation, objectivity, responsibility, and many others. Falsifiability can be used as a building block in a wide variety of TOK arguments. Actually, it's not as simple and as straightforward as I have presented here, of course. Falsifiability has its limitations, and falsifiability itself has been attacked as a scientific principle. There are important problems in science that seem to make falsifiability not suitable. For example, there's the problem of theory-laden facts. Every fact, every empirical observation in science already bears an element of theory in it, and that's inevitable. The question is then, how can we use observational facts to test theories if facts themselves are dependent on theory? And then there's the problem of incommensurability of scientific theories. It says that at any given point of time, there exists more than one theory that fits into the available evidence equally well. For example, think about the Big Bang model of the origin of the universe. It's not the only scientific model of the origin of the universe. And all the currently existing models are actually equally supported by the available scientific data. It's just that they're making different assumptions. The problem is then that observational evidence alone, and falsifiability for that matter, is just not sufficient for us to choose one of these incommensurable scientific theories. And we seem to be choosing them on some other basis. All this and more you can learn from our new TOK textbook, written for the new syllabus. However, don't open this book if you're not prepared for your mind to be blown and your life to be changed forever. See you next time.